we have now a situation where we have an ordinary differential equation similar to this one. We have the derivative of a function j multiplied by another function, and well, this is another function, lambda coefficient r of x, and multiplying by y equals 0. So we know that this ordinary differential equation is defined over an interval from a to b, and it needs to satisfy the conditions k1 times y plus k2 times y prime equals 0 when x is equal to a, and L1 times y plus L2 times y prime equals 0 at x equals to v. And this problem, or this this kind of a problem where we have an ordinary differential equation that satisfies these kind of conditions, and given conditions for the values of x equals to a and x equals to b, are called boundary value problems. And we then require to find eigenfunctions y of x that can solve the ordinary differential equation and satisfy the given conditions. How do we make it? We require to obtain the value of lambda, which is a eigenvalue for which an eigenfunction exists. What does this mean? Well, that we require to obtain a value of lambda called an eigenvalue, so that the given function y of x is actually an eigenfunction. And this means that this function, y of x, would solve the ordinary differential equation and satisfy the given conditions. We also have another concept. We know that the functions y1 of x, y2 of x, and so on are defined in an interval a to b and are called orthogonal on this interval with respect to a weight function r of x different to 0 and major to 0 if for all m and all, sorry about that, n different from m, we have that y of m yn is equal to the integral of av of rx times ym of x, or n of x dx, equal to 0 whenever m is different to n. So we know that the functions m and yn are orthogonal if they fulfill this inequality, where the given function is multiplied by the weight function. If we integrate it in the given interval, we will obtain 0 as a result. And we also know that the norm of a function jm is defined by the norm of y of n is equal to the integral of yn comma ym and the square root. So we know that this value is given by the given integral here. So we know that the integral is defined as the integral from a to b of the weight function r of x multiplied by ym squared, because we are it's like we have, instead of yn we have 2 times ym, so it's ym squared and its square root. So you can now make another definition. Functions y1, y2, etc. are orthonormal on the given interval if they are orthogonal on the given interval and all of these functions have a norm equal to 1. Then we can make another assumption. The evaluation of this integral by n of x dx would be equal to this function, where it is equal to 0 if m is different to n, and equal to 1 if m is equal to n. Now we will talk about orthogonal series in the generalized Fourier series. So we have the given functions y0, y1, y2, and so on, and we consider them orthogonal with respect to a weight function r of x on an interval that goes from a to b, and then let f of x be a function that can be represented by a convergent series. So let's have f of x equal to the summatory of m equals 0 to infinity of a m of x. Well, this summatory, and we will have a0 y0 of x plus a1 y1 of x, and so on. Then we can have this next evaluation of the given integral from a to b of r multiplying by f and y of n dx, as we have previously observed in this video. So this can also be represented as follows: r and the series that goes from m equals 0 to infinity of a m y m multiplied by yn dx. Thus we will have something like this: m equals 0 to infinity of the integral of a v r a m y n dx. And finally, another representation can be as follows: a m y m comma y m. So yep, this is another representation of the given series, and well, we can make another conclusion. Sorry, I believe I hear missing. Yeah, there you go. And now this inequality is correct. Now, because of orthogonality, the result of the previous integral will be equal to 0, as we have previously mentioned, except when m is equal to n. In this evaluation, sorry, this is not m, this is n. This is an n. Therefore, if that happens, then we will have something like this: the norm of yn squared. Therefore, the evaluation of the integral, for f and yn is equal to an multiplied by yn squared. So either we have a result equal to 0, or we have the evaluation of the integral using this inequality. Also, another consideration can be made: if all the functions y of n have non-zero norms, then we can obtain the coefficients of the series using this method. Ym squared equals to 1 over ym squared, the integral of a to b of r of x multiplied by f of x and ym of x dx. So in this way we can also obtain the coefficients of the given series, and thus we can also obtain the coefficients of a Fourier series, considering that f of x is actually a representation of a Fourier series. And that's all.